Okay, so we have physics Ph.D. qualifying exam, practice problem number 12 in electricity and magnetism. So let's begin. A toroidal solenoid has rectangular cross-section structure where the inner radius is A, the outer radius is B, and the height is H. The current is I, and the number of turns is N. Part A, using Ampere's law, determine the magnetic field everywhere. Part B, construct the vector potential A inside and outside of the toroid. Part C, compute the total magnetic energy stored. Part D, derive the self-inductance. And Part E, determine the limiting behavior. So this is a magnetostatics and vector potential problem involving a toroidal solenoid. So for Part A, the magnetic field, use Ampere's law for that closed integral B dot dl equals mu naught I sub ENC. And for a circular loop here of radius r, concentric with the toroid, b sub phi 2 pi r equals mu naught ni. So inside here, the b of r equals, mu naught ni over 2 pi r phi hat, and for A is less than R is less than B. And for an ideal toroid, our B is equal to 0, R is less than A, and R is greater than B, neglecting fringing. For part B here, vector potential, we choose A equals A sub z of R z hat. Then in cylindrical coordinates, B equals del cross A, and B sub phi equals negative d A sub z dr, that derivative there. Inside the toroid, negative d A sub z dr equals u naught ni over 2 pi r. And we integrate that. A sub z of r equals negative mu naught ni over 2 pi ln r plus c. From there, we choose A sub z of A equals 0. And then going back over here, then for A sub n, that equals negative mu naught ni over 2 pi times ln of r over A z hat, where A is less than R is less than B. And inside the central hole, R is less than A. We choose A equals 0. And going along from here, let's see if this holds up. Sorry. Let me take this over here. Sorry about that. And then for R is less than B, since B is equal to 0, A may be chosen constant, and A sub out, that equals negative mu naught ni over 2 pi ln b of A z hat. And this gauge gives the curl in the field region. Sorry about that, but the focus of the camera here. Part C, the magnetic energy. The magnetic energy is U equals that integral of B squared over 2 mu naught dV. Inside the toroid, B squared equals mu naught squared N squared I squared over 4 pi squared R squared. And the volume element is dV equals R dr d phi dz. Okay, so we have U equals this integral here from 0 to H dz, 0 to 2 pi d phi from A to B, 1 over 2 mu times mu naught squared N squared I squared over 4 pi squared R squared R dr. So U equals mu naught N squared I squared H over 4 pi times that integral from A to B dr over R. And after we integrate that, compute that, we get the following for U. U is equal to mu naught N squared I squared H over 4 pi ln B over A. For part D, the self-inductance, we're going to use u equals 1/2 Li squared. So 1/2 Li squared equals mu naught n squared I squared h over 4 pi ln b over a. And performing the computation there, in algebra, isolating L equals mu naught n squared h over 2 pi ln b over a. And for part E, the thin toroid limit, what we're going to do here is we're going to let b equal a plus delta, where delta is much less than a. So ln b over a, that's going to equal ln of 1 plus delta over a, and that's going to approximate delta over a. And therefore we could say L is approximately mu naught n squared h over 2 pi a times the quantity b minus a. Okay, so that's all for this one. Thank you very much and have a great day.